Oh my gosh. So the total conservation of conservation momentum, total momentum before and after a collision is equal. So the equation for this is momentum of object 1 initial plus momentum of object 2 initial plus any other objects that you have equals momentum of object 1 final plus momentum of object 2 final plus any others that you have. Now, that's kind of a long thing to write out every time. So there is a simpler way to write it out, which I'll give you as well. I'm going to give you this equation on the test. I'm going to give you this other equation on the test. I'm going to say, draw an arrow to show that this other one is 2. And it's written this way. Yeah, so this is the Greek letter sigma. And sigma means sum. So sigma means sum. So it's the sum of all the initial momentums equals the sum of all the final momentums. In other words, the total momentum before the collision equals the total momentum after. So the total momentum before is equal to the total momentum after. This is a little bit of an easier way to write it. It is this. And I don't want you to be confused by this one, so I'll give it to you both ways. But if you're writing down what equation you're using on a problem and you want to just write this out because it's simpler, you can do that.
So can I just put that on my notes? But I wasn't going to write all that long.
If you know what this is, yes. Like because to do this, you're going to have to do this every time.
So what does that say? 'Cause I really
So momentum 1 initial plus momentum 2 initial plus any others there are equals 1 final plus 2 final plus any others there are. Now, I told you there's another definition for conservation of momentum, which is the way that Newton kind of thought about it. And the way that he thought it was in the absence of an external force, total momentum change is 0. We'll come back to that idea a little bit later. So that's the other way to think about it. I'm fine with either definition. Either definition is correct. This is the way it's easier for people to think about, but this is the way that Newton thought about it.
Oh, is this like saying two things coming at each other, move, and each other stop?
That would be one way to think about it, yes. It doesn't have to be that exact situation, but that is an example.
That makes sense.
Yeah. All right, so what are inelastic collisions? So inelastic collisions conserve momentum only. An example of this is a car crash. So car crashes conserve momentum. So the total momentum of the two cars before they hit equals the total momentum of the two cars after they hit. So whatever happens before and after the collision has to be same. The overall momentum change has to be 0. So the total momentum before and the total momentum after have to be the same. Okay, so that's an example as like a car crash. If I say completely inelastic, I mean they stick together. So if I say something is completely or totally or fully inelastic, I just mean they stick together. So a car crash that's completely inelastic is going to be where the two cars smash into each other and stay together. Okay? For example, if you're driving down the road and you turn a corner and a garbage truck is coming backwards at 30 miles an hour and crashes into your car and gets lodged in your engine block, that would be an example. Not that that's happened to anybody like me, But that would be an example of a completely inelastic collision. And then lots of fun things happen after that, such as the garbage truck driver says, I can't believe this happened again. And I'm like, how did this happen once? You've done it twice? That anyway.
Do a picture of it.
On my old stupid phone, but it's not on one now. It was pretty impressive. The hooks that like pick up the giant trash cans were like ledged into my engine. It was pretty sweet. Needless to say, my car was totaled.
Did the insurance pay it out?
They paid. Yeah, they paid to fix it. It was like, I should rephrase it. It was like $30 away from being totaled. So because it wasn't totaled, they had to pay to fix it. So yeah, it was like almost totaled, and like they even had like 2 different opinions to see if it would get totaled, and it wasn't. So I laughed at them.
Wait, so if it does get totaled,
Then they just have to pay out the amount of your car's value. They just pay how much your car is worth, but they don't have to fix it. So now you have less money to buy a car that's not as good as the one you had. But if it's not totaled, they have to pay to fix. Like they had to pay to fix the car. So I got a brand new. Well, not a brand new. It was all used parts, but I got a new car essentially. All right. What are elastic collisions? So inelastic conserves momentum only. Elastic collisions conserve momentum and kinetic energy. Now, we haven't talked about kinetic energy yet, and we're not going to until next unit. So for right now, think of kinetic energy as motion. Yeah. Kinetic energy is your motion. So if you conserve motion, that means that the motion before and after has to be the same. Kinetic energy roughly goes with velocity. There's more to it than just that, but it roughly goes with velocity. So let me give you an example. Pool balls. All right, if you've ever played pool before, you've got the cue ball, which is the all solid white one, and then you have, let's just say, the 8 ball, which is the black one. Okay? If the cue ball comes in at, let's just say, 5 meters per second, and the cue ball is at rest, they have basically the same mass. So after they hit, it's an elastic collision, which means you have to conserve motion and momentum. Well, momentum is mass velocity. So 5 times the mass and 0 times the mass would equal to whatever the final momentum is. But motion has to be conserved, which means that what should happen to these 2 objects? If you've ever played pool before, you may know. What happens to the cue ball? It stops. It's going to stop. And now the other ball, the 8 ball, is going to move with the same speed that the cue ball had.
Oh, Mr. B, you ever seen that thing? You take like 2 basketballs or 2 tennis balls or 2 of the same balls, and you drop them, and one of them stays on the ground, the other one bounces up.
Right. Because that's an example of an elastic collision, roughly. The motion has to be conserved. So you have 2 objects falling at the same rate. If one stays on the ground when it hits, and the other one has to go up with double the velocity.
Both fall in 9.8 meters per second squared.
Right. And so now they're going up at double the acceleration, essentially. Yeah, so it launches one of them. It's particularly good if you do it with like a basketball and like a tennis ball. It just sends the tennis ball launching. Good. All right. Let's relate these to Newton's 3 laws.